Okay, hey everybody. So I see there's 13 of you so far in our class, so hang tight. We'll start about 10 minutes or so.
Mhm.
Hello, hello.
All right, so hey everybody, I'll go ahead and get started now. First thing I'd like to do is, so I see that there's 33 that are joined in our session here. Just to make sure that everyone knows how to do this, can you all press the indicator to raise your, have the little hand jump up and down? Okay, so it looks like most of you, everyone can do that. All right, so it may be hard for me to sort of immediately see that feedback. I'll try my best. If you do have a question, I believe you can unmute yourself, and so just feel free to do that. Otherwise, my worry here is I'm just going to keep talking, and half of you have questions, and I'm not able to address them. So we'll just have to get through that, or make sure I figure out how to get through that. Okay, so what I thought we'd do today is take a quick look at our web page, and I think I have things ironed out for at least the next couple of weeks. The material that I'll start going through today will be really just a high-level pass at the items that we'll be going through in more detail. And homework 3 will be out later today, and that will help with understanding what we're talking about. Okay. So, Mirwan, did you have a question? If you do, all right, I'm going to try and unmute you. My computer is not cooperating today, so I don't know what is going on. I'm having problems with my mouse. Okay, it looks all right. All right. All right, I'll continue here. Okay, so let's see. There's 1, 2, 3 things that I want to talk about. First, let's go to this page, information page on remote courses. And this is just meant to sort of put material or links to stuff that Clemson is making available. And so that's those first 4 links. And obviously everyone has figured out Zoom at this point, but that's the download site. And then Slack. If you're not using Slack yet, please do. I'm going to figure out a way to see how many in the class are on Slack so that I can use that for messaging instead of Canvas. All right, so online class, just some points here. At this point, I'll post the link and the meeting ID out through hopefully Slack, but I think I'll always be using the same meeting ID. And if that changes, I'll let you know. When you join, I have seen that everyone is muted by default. Last point, have patience. Okay, we'll get through this. All right. I guess another point related to questions that you may raise through, like a chat message. So go ahead and ask a question. If you do have a question, we could use this as well. If I don't see it sort of in real time, I may have to get to it like after the session, but if you have questions, I'll definitely see those. And so that might be a reliable way for you to give me feedback and or ask questions. All right. So that's related to our remote process here. Okay, the next thing I wanted to talk about was the project. And so I posted this information a little while ago, which was meant to give something more concrete in terms of, what the expectations here would be for the project. So if you haven't looked at this, do look at it, and there shouldn't be any surprises here. I think I've sort of set all this up talking about it in the past. I am a bit more specific in terms of how we're going to grade things. We've broken it up into 4 milestones, and the first milestone, I need to go back at the schedule and see if the date is correct or not. It's basically, you're going to give me a summary of what you plan on doing, and the way I see this sort of working out is once you form your groups, and I'd like that to occur today at the latest, send me an email and CC Anurata and Manveen as well. So I'm after the team members in your group. Why don't you go ahead and pick a name for your group? And then I'd also like you to select one of the 4 in your group to be the leader. And that will just make things easier for me if I need to talk with the group. So I'll have a single point of contact. So let's go back to my view of everybody. So if you do not have a team at this point, raise your hand. Click the thing to raise your hand. Okay, and so maybe via using the messaging, online messaging, go ahead and try to form teams, and you could do that sort of while I'm talking here. And so again, we're looking for groups of 4, and let me get back to a rough discussion of, or some examples of projects that you might do. I realize that we really need to be careful in terms of the scope of any project, and so if, let's see, if I'll just go through these sort of one at a time here. If your group wants to talk about any of these in detail, then we can set up a time to have a Zoom meeting and talk. I think it would be much easier for me to talk with one group at a time, and so we'll set that up. peer-to-peer broadcast messaging system using UDP, so sort of like a chat room. Okay, sort of in a similar thing. There's a way of communicating that's different from client server called publish subscribe, and it's basically a way for groups, so one to talk to many. The number 2 there, see that shaking there that you see, that's my computer going crazy. Number 2 there. So we're going to start talking about pipes today, and it might be a little bit more clear after we get through that, but there's I think an interesting project where you make or develop a sort of an abstraction layer for pipes. You can do a C++ or Python version of our UDP Echo version 3. You could do some sort of an extension to that code. One possible extension to UDP Echo would be if you take a look at some of the material that is out that talks about this thing called QUIC. So Google came out with, it's effectively a new transport protocol, and it was originally designed to improve web browsing because TCP has some issues that cause response times to be unnecessarily slow. And QUIC is based on UDP and it implements aspects of TCP. And so in past classes, I've had student projects where you implement with UDP aspects of TCP. And again, we're going to be talking more about TCP, so that might make more sense in a week or so. Okay, a simple UDP or TCP filter whose job is to allow a Linux pipeline to extend across a network. And so we're going to be talking about Unix pipelines a little bit today. And so that will give a little bit more information. But the idea here is to do something similar to tools like NC or NCAT or SOCCAT. Those are sort of 3 commonly used Unix utility programs that allow you to basically extend a pipeline across a network. And then if you have your own idea, that's fine. We'll talk about it. All right. So that's what I wanted to say about the exam. Material, all right, the stuff that we're going to be covering at least for the next couple of weeks. So I put together a page that tries to capture that. And I'll begin going through that. Before I do that, let me say that Manveen will be doing a virtual help session, so via Zoom, and she'll send out the meeting ID or the link for that. What we're going to try and do in time for that session tonight is we have the tests, your exams graded, and we're going to scan them and send them back to you. So, ideally we get that done before the session tonight so that if you have any questions, you can ask. But if it doesn't go well, then we'll have that back to you by class time on Wednesday. All right. So there's a lot of words here. Don't let that intimidate you. It's I'm trying to be super organized here in terms of sort of putting into a box here what we're going to be covering the next couple of weeks. And topically, we could reduce it to this. So we're going to do an overview of Unix pipes. We're going to talk about networking concept, transport protocols, and then we're going to talk about 3 specific transport protocols: UDP, ICMP, and then TCP. The reading for all of this is, I think this more or less captures it. So in Donahue, chapter 2 shows basic TCP socket programming, and so that should be helpful. The programs that we begin with are really based on stuff from chapter 2. Chapter 5, 6, and 7 talk about slightly more advanced items related to sockets and specifically TCP. So make sure that you look at those chapters. And then in the textbook, chapter 3 covers transport protocols. And I would recommend reading the entire chapter 3 because it's very good. It is a little
Dr.
bit long.
Martin.
Yes. Yes.
Some people are wondering if you're going to be doing test corrections this time.
Let's see, test corrections. So what do you mean? You mean if you have questions on how we graded?
I think some people were just wondering if you were going to do anything similar to the last test where you gave the test back and they could correct questions that they missed.
Oh, I see. Yeah. I'm assuming no, because everyone seems to have done pretty well. I don't think we've posted the scores yet. Is that correct?
No, the scores are up.
Oh, the scores are up. Okay. So at this point, no, but I will consider it. Is that a did I beat around that question?
That's good. No, that's good. Thanks.
All right. Yeah, you bet. Thanks for interrupting me, by the way. So I think that's going to be the way to do this. Is if you have a question, unmute and get my attention, because otherwise I can't sort of track. When people are raising their hand or chats or that kind of thing. So, all right. So let's see. All right. So yeah, the last thing I was saying was chapter 3 of Kurose is very good. It contains all the information that we're going to be interested in. Oops, snap. All right. And you're seeing me on video now. Lovely. All right. So let me get back to all right. So we're going to start talking about pipes, Unix pipes, and I need to move these links into that page of material for the next several weeks that had the list of reading material. This is good background. It's fairly short. You could just go to the section on pipes and FIFOs. And this should be supportive of the things that I'll be talking about in our lecture here. All right, so okay, so I thought I would begin sort of in part with a review of some terms and then introduce some terms so that we sort of clear up any, gosh, this thing is going crazy, any confusion here as I begin to walk us through some of these PDF lecture notes. All right, so I believe at one time we have talked about the term bandwidth, and that was probably when early in the class when we were talking about the physical layer, link layer, so the lower layers of the OSI networking stack. Bandwidth, the correct definition of bandwidth is it's a measure of the raw information rate of the underlying physical medium. And so it's typically measured in units of hertz. So for example, an Ethernet cable or a, like for cable access, there's coaxial cables. The bandwidth for those physical mediums is roughly 2 gigahertz. And all for those, for Ethernet or, well, for Ethernet, all of that bandwidth is made available to all users that are sort of competing to use that shared medium. There's other communication technologies like Wi-Fi where there's actually multiple blocks of raw bandwidth in the spectrum, in the RF spectrum. And so in particular, Wi-Fi uses blocks at around the 2.4 gigahertz area and the 5.0 gigahertz area. And the way Wi-Fi is designed is it breaks up that large block of spectrum that's allocated for Wi-Fi at either 2.4 or 5.0 into smaller blocks called channels. And the size of the channels can be 20, 40, 80, or 160 megahertz. Okay, and back early on in the semester, we talked about like the Nyquist theorem, which gives for a given bandwidth, like 20 megahertz or whatever, it tells us the absolute maximum data rate that one might get from that bandwidth. Okay, so that's the idea behind the bandwidth and then channel. Data rate is a term that, again, is many times misused. So imagine the link layer and its job is to get data from above. So, if it's IP, the link layer is placing IP datagrams into a frame, and so there's quite a bit of overhead as going from an application that might issue a send. So there's a block of data at the application level, and that goes down the stack into the transport layer where a header is added. That then goes down to the IP layer where the IP header is added, and that thing would be called the IP datagram. And then the IP layer then forwards that to the link layer where a MAC frame is created. And so the data rate would be the rate at which digital data bits can be sent over the channel. And so there's some complexity there, but it's just, for our purposes, it includes all of that overhead. Okay, and then the next term, application throughput or goodput, would be the rate at which application data can be sent over a channel. Okay, that brings us to the topic of transport protocol. So we've defined this in the past. So the transport protocol is the software that is sitting at these socket endpoints, and applications interact with the sockets layer, which effectively allow it to engage the transport protocol. Okay, so next term is pipe. And so there's, depending on the context, there's two different definitions or way to think of this. So in a Unix context, pipe means something very specific. It is a form of inter-process communication. And so, my example there is, if you do issue a command find, and you give the starting directory location that you want the find to begin looking for things at, dash, you can do dash name and then in quotes the name of a file, or dash type, where P type would be if the file you're specifying you want to find all files of a certain type, whether it's a regular file, a directory. P would be a linked file. And then the action from what find finds is the dash ls. And you could find supports many actions. So it's not just listing. You could do quite a bit with the find command. But our point here is just to show that that is a pipeline. The output of the find is being piped to the input of the command word count, WC. And so the way the shell carries this out is going to be very similar to some of the code examples that we're going to look at on Wednesday, where the parent process creates most likely two child processes, and it creates one or more pipes that allow, effectively it's going to use the pipe that's created, and it's going to redirect the standard out of the first child process. Let's say that's the one that will have exec the find command. So that standard out is redirected to this pipe. The child process 2 is running WC. Its standard in is redirected to this pipe. So this pipe, a pipeline, allows the standard out to go into the standard in of the series of programs or filters or scripts. And that's all standard Unix pipes. Okay, in a networking context, so the notion of a pipe, and we have talked about this as well, think of it as it's the socket. It's the instantiation of a socket, a communications channel between two instances of a program. And so there's data flow over that socket. Maybe visualize a pipe, right? That where the endpoint is. I'll use in the writing there, I use the example, host A is communicating with host B, and let's say that host A is sending data to host B. So that we can picture that and call that a pipe, and it actually is a flow over the internet. Okay, but the concept of a pipe is, again, sort of an abstraction that is useful. So this gets us to the notion of pipe size. So again, for the networking term pipe, the pipe size would be, again, sort of in your mind's picture, literally a pipe between host A and host B. And the size, the pipe size, represents the maximum amount of data that can be in that pipe. Okay, so the reason why there can be data within that pipe is because it takes a while for data to propagate, right, from a sender to a receiver. So the longer the propagation delay, the larger the pipe size will be. So the pipe size is effectively the volume of data that can be sort of in transit between the two endpoints. And another word for that is the bandwidth delay product. That's equivalent to the pipe size. So the bandwidth delay product, we'll use this example here. Let's say host A is communicating with host B. Let's say it's running, that flow is running over a path that involves, multiple networks, the public internet, and the effective data rate that is available to that flow, let's say, is 10 megabits per second. And let's also say that if we do a ping from host A to host B, host A sees that the average round trip time is 10 milliseconds. So the bandwidth delay product, which gives us the volume, the maximum volume of data that could be in the pipe, is literally, gosh, this is so annoying, is literally take the bandwidth or the effective data rate, multiply it by the average round trip time that is observed. And so in that, our example, that would be 10 million bits per second times, so that's the bandwidth, times the delay, and we'll use the round trip time of 0.01, 10 milliseconds, and then we'll convert from bits to bytes. So we'll divide by 8, because in 1 byte there's 8 bits, and that leads to 12,500 bytes. Okay, so why is that important? Oh boy. When we start talking about windowed transport protocols, we'll see that the ideal window size is going to be the BDP. And when we start talking about TCP, we'll see that its sort of dynamic algorithm to use as much bandwidth as it can, what it's trying to do is it's trying to set its window to the current BDP over the path. Okay, and again, we'll go through examples and talk about this much more. This is more just sort of setting up the discussion. So to introduce transport protocols, these are the typical functions that one would identify as being a part of a transport protocol. So first of all, the communications paradigm is sort of independent of this discussion of transport protocols, but it's important to keep in mind. So two programs can communicate unicast, so that's one client to one host, and that's pretty much what we have been playing around with UDP Echo. Broadcast, so that would be one client sending using a broadcast address so that all stations on that network, if they're listening, could receive the message. So it's all to it's one to all is that paradigm. And then there's something called multicast, which is actually an internet protocol, and it allows a group of nodes to join a multicast session. And so it would allow one sender to send to all listeners or receivers in a manner that does not, it would attempt to be as efficient as possible. So it would not require unicast. So the single sender to all the recipients, it wouldn't require a unicast session to each. It would try to send in a unicast manner as far along the path as possible before the multicast tree sort of breaks. And at that point, then unicast to individual endpoints might be required. Okay, so those three models are sort of fundamental to any and all types of networking, but they do come into play when we talk about transport protocols, and we'll come back to that. The second bullet there, transport paradigm. Okay, so here we just will simplify things and say the transport can be one of three types. And this is a TCP/IP discussion. A datagram, which would be a UDP type of transport. A stream, which is a TCP type of transport. And other. So like the Internet Control and Messaging Protocol, or ICMP. Okay, so those are the 3 standard transport protocols in the internet. There are other ones like that QUIC protocol that I talked about from Google. So that is considered a standard transport. I have my smartphone in front of me, and when I mention Google, it's asking me what I want. Oh, Google, you're so creepy. Okay. Okay, so congestion control, a transport protocol might provide or support congestion control, or it might not. And when we talk about UDP, it does not support congestion control at all. When we start talking about TCP, we'll see that TCP does support congestion control, which means that if it detects that the network becomes congested, which means packets are being dropped, TCP will reduce its sending rate. The next bullet, sending scheme. Okay, so this is sort of similar to UDP versus TCP, but it's more generalized. So the sending scheme of a datagram, so that means something very specific. Every single send to is going to create one IP datagram. If we use the stream model like TCP, then with the send, we can actually have in that buffer a very large amount of data. And things are more complicated with TCP because there's a socket buffer involved, and we don't want to send so much data that it overflows the buffer. And so we'll look at code that does, let's say that there's 10 gigabytes of data to send from host A to host B. We'll see code that loops sending a chunk size of that data at a time until it gets through the entire 10 gigabytes. Okay, another aspect of transport protocols is what I call the rate-based or window-based. Okay, so this typically comes into play with streamed-based transport protocols. So TCP is a window-based protocol. And so, let's define a window as, to a transport protocol, it's the number of bytes it's allowed to have outstanding in the pipe before it receives an acknowledgement from the receiver. And so the way TCP works is new data is sent out as acknowledgement messages arrive. So they're sent by the receiver and they arrive at the sender, and that clocks out new data. Okay, so that's a window-based transport protocol. There's another type, rate-based, where the transport protocol has a target sending rate, and it sends data at that rate. If there's a congestion control mechanism in play, feedback would cause the sender to reduce its target send rate until the congestion passes. Then it would go back to where it was. Okay. All right, 2 other attributes or concepts related to transport protocols: error recovery and error detection. So let's talk about error detection first, because they're 2 very different things. So like with UDP, okay, UDP has an optional checksum in the UDP header. In Linux, by default, it's on. So that means that when UDP, the transport protocol, gets data from an application via a send-to, it takes that data, adds the UDP header, and when we'll look at the protocol header later in the week, but there's a field that is for a checksum. The checksum is basically a mathematical computation. It applies it to all the data in the message, including the UDP header data, and computes a 16-bit number. At the receiver, when it receives that message at the UDP layer, it will also compute the checksum, come up with a number, and then it'll compare it to the checksum that's in the UDP header. If they're the same, then presumably a bit error has not occurred and the data is okay. If they're different, then an error has occurred and UDP will, at the receiving side, will drop that packet. So that is error detection. It doesn't recover. Okay, so error recovery, which is what TCP adds, would be, it would tell, the receiver would tell the sender that a packet was lost, and the sender would retransmit. So with TCP, it's a reliable connection. All right. I've probably talked more than what you could all bear. So my suggestion here is I'll sign off, but do begin. So for Wednesday, the next couple of days, work your way through this material. You'll see homework 3 out, which will be fairly small. It's not going to take a huge amount of work, but it will be very supportive of the things that we're talking about here. And on Wednesday, we'll dig deeper into the first topic will be Unix pipes. And I think with that, we're good for today. So I don't think I lost anybody here. There's still 42 of you. That's what the starting number was, so that's good. I hope you all are doing great. Hope you had a good spring break. And I will talk to you again Wednesday, class time. And again, feel free to contact me regarding anything. All right, that's it. Talk to you all later.